So our last area that we're going to talk about in here is column buckling. We finished up beam deflection last time, and we'll go into column buckling, talk about some of the theory today. Then we have one more lecture that deals with examples and practical problems, and that will wrap it up for the subject and for the term and then for the year. So if we look at column buckling, basically we are talking about slender poles or columns or slender bars that are loaded in axial compression. So you have something like this, and it really doesn't matter what the cross-section is. It could be a square cross-section, could be a round cross-section. This is a lot different than if we have axial tension. With axial tension, we don't have to worry about buckling. With axial compression, we do have to worry about buckling. So we should probably, to start a discussion on buckling, we should talk about types of equilibrium. So let me document this. So thinking about equilibrium, and we could make this discussion if we were talking about a chemical equilibrium or a thermodynamic equilibrium, or really you may have heard this discussion in math or physics or chemistry, but I'll reiterate it. We could have a stable equilibrium, and the analysis of that, or this oftentimes will be given an analogy, is a ball that's at the bottom of a valley like that. So if we have a small displacement, if you were to displace this ball sideways one way or another, it would return to equilibrium. So that's stable. Then we have neutral, where we might have the same ball, but this time sitting on a perfectly level, perfectly flat surface. Where if I have a small displacement, I come to a new equilibrium, but it's at a new point. So I displace it a little bit to the right, it comes and stops at the right and is at that new equilibrium. And then we could have a situation where it is unstable. So unstable would be the ball sitting at the crest of a hill, where we just got it to balance there, and any displacement is going to move that continually away from that equilibrium. So I wanted to look at this in terms of this column buckling and talking about this load P here. If P is small, we have a stable situation. If P is very large, and maybe we would say too large, we'd have an unstable situation. And if P is critical, the transition, we'd have that. So as it transitions from this to that, we have that critical value. So it'd be nice for us to be able to figure out what that critical is, so we would know what the difference between our unstable situation is and our stable situation. Now we should probably note that we also need to check just plain old compression. And usually if you have a very, if the member is very thin or very long, you're probably going to have buckling problems. If it is very short or squat, then you're probably going to go back to just simple compression, where you look at sigma is equal to the force divided by the area. So we don't want to forget that either. Okay, as we start looking at this P critical, which can get kind of complex, we don't want to also go back and remember to check this one. Well, let's get started on coming up with this, and this is why we saved this to this point in the term. I mentioned as you were going through your bridge design, a lot of you will have buckling problems, and I tried to give you some hints on this. The reason we didn't study this before is we actually needed to study beam deflection so that we could come up with these equations. So we'll do that. And I think I will maybe draw this on its side. So I'm going to take a pin here. I'm going to say that I have a pin at both ends. So we'll fix this like this, and maybe we'll put this pin on a set of rollers so we can slide that along, and we'll apply some load to this thing, P. you could imagine that this would be under compressive loading. And if I were to maybe draw this in a slightly deformed fashion, you could imagine anyone that's maybe taken a yardstick and applied a compressive load to it, kind of played with how it buckles around, recognizes this shape, where we would have something like this. Sorry for our foreign friends here, metric meter stick too, right? Okay, that'll tend to buckle a little more because you've got 3 extra inches there. But anyway, if I look at this, I could look at the left-hand side and say that we have something like this. And this deformation here, so we'll put that load P there. We'd, of course, have some internal force there. And we have a distance here, and that distance we're going to say is the deflection V. Okay. And we should probably talk about a moment then, and we could say that this moment here, summing the moments about the cut point, setting that equal to 0, I have the moment from slicing that in half minus the force P times that distance V, right? The more that deflects out, the more it tends to buckle. Anyone again's played with that yardstick or meter stick recognizes that. So I could solve for the moment M and say that that's equal to P times V. And it's kind of a vicious circle. As that deflection gets larger, the moment gets larger, and it tends to, as we saw in the first, become an unstable situation. Well, we have an expression for the moment. We could say that from our previous work, didn't we say that the moment was equal to minus EI times V double prime for the deflection of a beam? So let me set that equal here. I could say then that minus EI V double prime is equal to P times the deflection V. And I could rearrange this a little bit. I'm going to say that it's P times V plus EI V double prime is equal to 0, essentially moving the left-hand side to the right-hand side and then setting it equal to 0. And maybe I'll rearrange this a little bit more. Use some space over here. And I could say then that V double prime is equal to, or in addition to, let's see, solving for V double prime, I could say that that was P divided by EI times V, right? Is equal to 0. And I could let P over EI, I'm going to say that's equal to K squared, a constant, K squared. So I'm going to then rewrite this as V double prime plus K squared times V is equal to 0. You have a name for that equation? A lot of you are in Math 256 should probably have a name for that equation. Homogeneous, linear, differential equation. Yeah, it's a linear homogeneous differential equation, isn't it? Those take on a variety of solutions. This one probably has a solution here that V, the deflection, would be equal to A times the sine of Kx plus B times the cosine of Kx. Have you used that form for solutions? Probably fairly early on this term. That was a fairly easy solution. And I need some boundary conditions. It's all about boundary conditions coming up with A and B. So if I look at my boundary conditions, I could say that the deflection at x equals 0 is equal to 0. And that would net that B would be equal to 0. And I could then also say that the deflection at x equals L. So here x is equal to 0. Here x is equal to L. Well, the deflection at x equals L is also equal to 0. So that nets something that's a little more interesting, that 0 is equal to A times the sine of K times L. Okay? So let me take that onto the next page and continue to work with that. I'll also need to remember as I go to the next page that K squared is P divided by EI. Questions thus far? Well, we'll continue on then. So we said that 0 was equal to A times the sine of KL. And I also wanted to remember that K squared was equal to P divided by EI. Well, looking at this, this has a couple solutions, a couple ways to make that equal to 0. I could say that A is equal to 0. That wouldn't be particularly interesting. Or I could say that the sine of K times L is equal to 0. That's more interesting because the points of interest so looking at the points of interest there would be when KL is equal to what? Pi? Or maybe I should say n pi, when n is equal to 0, 1, 2, and so on. So I now have the solution to that differential equation, which is this. So I could say with K times L is equal to n pi. If I look at K squared L squared, that would be equal to what? N squared times pi squared, squaring everything on this equation here. And then what does K squared? We have K squared up there, don't we? So that's P times L squared times E, or is equal to EI. So I just multiplied both sides by EI when I substituted that in, times N squared times pi squared, right? Or I could say that P, solving for P, is equal to N squared times pi squared times EI divided by L squared. Okay? So that's worth looking at. That's our equation, and we'll see some slight differences in that, but they're all going to come back to that. So we could say that the critical is equal to N squared times pi squared EI divided by L squared. Okay. Where E and I, Young's modulus, area moment of inertia, of course we know what pi is. L would be the length of the column. And N, that's the only thing that may be a little bit confusing to see what that relates to in a practical sense. That's the mode shape. So if we look at a column that is loaded like this, that would be N is equal to 1, the first mode shape. If we look at a column that does something like this, that would be N is equal to 2, second mode shape. You might say, well, we'd never get to second mode shape because it would fail at first mode shape. And that's true to some extent, although we might have a column that is, let's see if I can do a rectangular column here. We might have this braced in one direction and not in the other. So it might take on second mode shape in one direction and first mode shape in the other direction. That's why we look at this. If we look at the units on this, we have N does not have units, pi doesn't have units, E will be in terms of pounds per inch squared psi, I probably inches to the fourth if we're using English units. And then the length, you're probably going to be tempted to use the length in feet, but if you do that, you're going to have to convert. Let's say that the length is in inches. So I'll have inches squared, and we come up with pounds, which would seem like a proper unit for a critical load. Now, we change this equation a little bit. So those of you that go into practice will probably look at the equation a little bit differently. And you'll say that our critical is equal to, you'll leave the n off and you'll just go with pi squared EI, and then you're going to divide this by this term KL quantity squared. Okay, so how much did that change? Well, what we did is we got rid of this n term up there and we added this term with L down here. So we changed that a little bit, and this is known as our effective length factor. The effective length factor. So this is a little more common way to look at the equation. Those of you going to structural engineering will probably see this quite a bit. If we do a units analysis, you'd have exactly the same thing. Let's look at some typical cases. If we look at a pinned arrangement like we started with, so we would have something like this and the load pushing down there, and we've got some length L. This we'll say is pin. K is equal to 1, like we did in our derivation just moments ago. If I look at something maybe like a fence post in the ground, so we have something that's fixed here and free on the top. So it's fixed at the base, it's free at the top. K is equal to 2. And hopefully that makes sense, because you could really think of this thing as being twice the length and having that there. If you look at a fixed on both ends, so it can't rotate at the top, it can't rotate at the bottom, and then we put the load on it like this. So maybe this is in some sort of a loaded situation where it can't rotate, but it could still go up and down. This is fixed, and K would be equal to 1/2, because it's going to tend not to buckle very readily. One that comes up quite a bit is something that looks like this. Where you have fixed at the base and you have pinned at the top. So it can't, this one was free, it could move either way at the top, horizontally. This one can't move horizontally at the top. And we have a length L, so this is fixed, pinned. And K in this case would be about 0.7. I say about 0.7 because you actually come up with a differential equation. There's not an analytical solution to it. You'd have to go with a numerical solution. So you'd get an approximation, but it's pretty close to 0.7. I brought in a table here, right here, of some of these things. Let's see, we were on page 5, so I'll say this is page 6. So this is from the American Institute of Steel Construction. They've got their steel design handbook. Those of you going to structural engineering, civil engineering next year will definitely have one of those. And that talks about different types of columns and the theoretical value for K. And then we realize that not everything is perfectly theoretical, so it talks about what your recommended value is. And you can see that with this equation, if the larger K is, the lower the critical value. So if we want to be conservative, we would assume K larger than it actually is. So in this case, where K is 0.7 that we just talked about, they would go up to 0.8. Or when they have K is equal to 2, they'd go to 2.1. So that's just some of their recommendations. So this is very practical stuff. Let's look at a I'll jump back to page 5 here. But let's say that we have a glulam beam like this, and we've got a beam pocket there, and we've got this column coming down. We maybe have a base plate attached into a footing with some anchor bolts like that. What would you say the K on this is? This is where you'll make all your money, because I've seen lots of columns and none of them have ever had the K marked on the side of them. Okay, so you have to look at it and say, oh, let's see, based on what I know, I'm going to take K as such and such. Well, what do you think? Fixed? Well, I haven't described this very well, but this base plate here is pretty thin, isn't it? Let me, since someone said fixed, I'm glad they did. Let me look at a different scenario. So we have this beam, maybe we have a much larger connection up here. Maybe we have a big gusset here. Okay, and this comes down to a very thick base plate that's anchored with some great big anchor bolts into that footing. Maybe we put some gussets on here. Or I guess the question now is, are these different situations? Yeah, I think you can imagine if you put this gusset in here and these gussets here and they have this very thick base plate, this is going to resist rotation, this is going to resist rotation, and you may well have a fixed. But thinking about that, if we go back to this one here, what would we have here? I mean, if we look at the base plate, and with a thin base plate, as that starts to experience some deformation, what that base plate will tend to do is actually deform like that. Okay, without those gussets on it. So could we think of this as a pin? Yeah, I mean, there's no pin there, but it's going to behave very much like a pin, probably way more so than this. And up here, I don't have a lot of gussets. Could we get some bending and some rotation up there? Probably. So I would think that we probably have a pinned-pin connection there, in which case we're going to be what? 1.0, whereas what were we if we were fixed? K is equal to a half, or from our table here, let's see, if we are pinned, that's that one. If we are fixed, we're a half, or maybe 0.65. Okay, so you're going to make all your money figuring out what K is to some extent if you go into column design, because there's really no money in calculating this equation here. They can come up with a spreadsheet that'll do that way faster and cheaper than you can. But going out, knowing where to look, crawling around in the attic and the insulation, and trying to figure out, do I have this or do I have that? That's what's going to keep you employed as a structural engineer. So some things to think about as we go through this. We'll put this equation in practice, and like I said, we'll look at a situation where it has different loading in two directions. In one direction, we'll see a different effective length factor than the other direction. So that's what we will do next time on our last lecture. Go through an example and get this finished up. Take care till then.